Yeah, thanks everybody. Thanks for joining me here today to discuss geoscience at massive scale. First to get a picture of my audience, who here does geoscience in general? Who here knows about geoscience? That's a few people. Others are just curious about what the hell I'm talking about. That's good. Who here knows Dask? That's more people. Okay, interesting. Today we're going to discuss Dask in the application of geoscience. And without further ado, let's just jump into doing some geoscience at large scale. For this, I've just, first and foremost, because we're doing large scale stuff, I've just spun up a cluster that's 100 machines, spun this up on Coiled, which is also my employer. We just do managed Dask. So if you ever want to deploy stuff, feel free to talk to us. We're just loading a pretty big data set. It's a national water model from the Office of Water Forecasting in the US. It's some geospatial, some geoscience data set. Yes, that is a very good point. Let me zoom in here a bit. What we can see here is, this is a fairly big data set. It's 250 terabytes. For demonstration purposes, we're actually not going to crunch all of that data, but instead what we're going to do is we're going to take a smaller subset of that. It's still 12 terabytes of data, so we're still crunching quite a bit. But this will help us get this done in a fairly short amount of time. And what we want to do here as computation is we just want to calculate the mean depth to soil for every county in the US. So we're just doing some additional data loading here. The interesting bit is here. So what we do is just we're calculating the mean for each of the counties that we have in the US. The output data set will just be like 140 megabytes, so condensing it down quite a bit. Let's just try that. So I'm firing off the computation here. This will take a moment until we get this data onto the cluster. And now we can see, okay, we're starting our computation. We see here actually that it's like 70,000 tasks. It's quite a few. Things are progressing. Up here, we see a lot of activity in this task tree, and that just tells us we're making progress towards our goal. Workers are doing stuff. We have quite a bit of data on the cluster. So right now, it's 3.5 terabyte of data loaded into memory on different machines. Some of that data we've actually started to spill onto disk to make sure that we don't run out of memory, because that's usually bad. This now continues for a few minutes. While this just goes on, let's talk about a few different other things that we can take a look at while this is running in the background. So since it is cluster computing, since it is distributed computing, what we can also do is go to just say the Coil dashboard and see, well, what's the activity on our machines? Here the scheduler has been up to quite a bit of stuff. Actually, probably more interested in workers. Are they actually doing things or just hanging out? We see here as well, they're doing quite a bit. All of this up here, that's the gap where I had already spun up the cluster, so don't worry about that. And we see different metrics here about what our cluster is doing. We can also, if we're interested in that, see some logs from the workers. And in the meantime, this should have, made its way almost toward the final end of the computation. What I'm showing you now, that's plain Dask. That's the open source version. If you ever spun up a Dask cluster, this is what you'll be able to see. This is actually the default view. There are other views. You can dive into more detail on the workers. But also, if you want to have even more information, that's where things like managed Dask on Coiled come in. Now, finally, yes, this is finishing up in 3, 2, 1. Now it's done. So yeah, we've computed small amount of summary statistics from a huge amount of data. We can now visualize this, and what we'll all see in the end is this nice picture. So we've just processed 12 terabytes of data for roughly $2 in terms of cloud computation. That's quite good. And this is the sort of computation that geoscientists, or like at least some geoscientists, do in their daily work. So let's talk a bit about libraries that we've been using here to actually be able to do this. First and foremost, let's talk about Dask. I've mentioned I kind of do Dask things. I'm actually a maintainer of Dask, so that's the main thing I work on. Dask itself is fundamentally a library for general parallelism in Python. What that means is you can just parallelize pretty much any computations that you can express in Python in Dask. So whether that's sort of this embarrassingly parallel for loopy stuff where you just want to process a bunch of files, you can totally do that in Dask. But it also has some nice integrations into the PyData ecosystem. So if you want to scale out your data frame computations, your pandas computations, there's an API in Dask for that, where we then just help you scale this out to terabytes of data. Similarly, if you want to scale out your NumPy computations or similar things, once again, we mimic the API of that, and you can then run this on much larger data sizes that you would be capable of on your local laptop. But since it's a library for general purpose parallelism in Python, you can also use it to parallelize and distribute whatever complex custom workload you have. So what you see up on the upper right here is that's actually a task graph of computation from an actual Dask user, which is custom built, is pretty complex. So it goes far beyond things like the average, say, MapReduce paradigm that other systems are built on. The second library I want to talk about with you today is Xarray. If you don't know Xarray, in a nutshell, it's NumPy but with labels. If you've used NumPy, we all recall that you have like multidimensional matrices, and like you have to remember that x is 0, that's actually time, x is 1 is longitude, x is 2 is latitude, and also the slice at value 150 of time that corresponds to the 1st of September 2020. That's all a bit difficult, so people have built Xarray, and it's a great library. We saw some of that awesomeness already here. This is where we loaded the Xarray dataset, and what we see is suddenly our axes have a meaning. X is 0 is time, x is 1 is y, well, could have picked a better name. But not just that, we also see that the values along those axes now have a meaning. So this is not just the first index, but it actually corresponds to this particular date in time. And Xarray allows also a few more things. You can actually group different matrices together. We've also seen this here, so temperature and precipitation would belong to the same dataset. It's a pretty nice library. If you don't know it, check it out. Now, where the real magic comes in if we talk about geoscience at massive scale is when you combine Dask and Xarray. Because what happens then is, as we've just seen, you express your computations in Xarray, but it under the hood then creates a Dask task graph, submits that task graph, this distributed computation onto a large cluster of machines that you've spun up, well, anywhere. You could have used Kubernetes, you could have just spun it up with Dask Cloud Provider on AWS, or even used Slurm if you have an HPC cluster lying around. And yeah, if you don't want to deal with too much of that, there's obviously also coiled. Pitch ends here. What this does is, we've seen it, helps us distribute the computation onto large numbers of VMs. We can easily access data that's already stored in the cloud. We don't have to move data from the east side of the US from a particular AWS data center onto our Paris notebook. but instead we can just spin up the cluster right next to the data and things get a lot faster. So that's to set the stage here about Dask and Xarray and how those tools allow us to do geoscience at scale. When I initially set out and wrote the abstract for this talk, I thought this would be a walk in the park, and I thought I'd just tell you how amazing all these tools are together, and this would be a breeze. Everybody would love it, it would be great. Turns out it still has a couple of problems here. And this is what we're going to talk about today. So recently, at Coiled, we've invested some time into improving the array API and improving computations run on distributed arrays. We'll look a bit into this, and then we'll also talk about geospatial benchmarking, why that's important for us and why that's important to drive the future of geoscience at scale with Dask. Now, the first thing I want to talk about here is rechunking. That's a very notorious thing you have to do while processing multidimensional arrays in a distributed engine. Because as we've seen, like, data sets are huge. So 12 terabytes that we just processed, they don't fit into memory on a single machine. So obviously we have to chunk this down into tiny bits we can hand off to each individual computer and then make sure that they can run some sub-computations and combine those results back in the end. The most pathological case here is if you have to rechunk a data set from space to time. So think about a data set of one satellite image per day. It's stored this way. But what you actually want to do is do some summary computations over all of time. You want to say, give me the mean value for each of the individual geographical points on there. Now suddenly, each of those images provides like one bit of information for the summary statistic that we want to calculate. And this is a huge problem, or has been a huge problem in Dask. The gist of it is, once again, every input contributes to every output. So Dask would create a Cartesian product of all those things and would just have a huge amount of intermediate tasks that are very small, that overload the scheduler at some point, and generally would limit its ability to scale. What we've done in Dask is we've now introduced the P2P rechunking method that's enabled by default in some cases where it's actually helpful. And this system just uses the task-based paradigm that Dask has for concurrency control and coordination, and does all the data transfer, all the actual computational stuff. It does that in a dedicated subsystem that, that does its thing on its own in an out-of-band mechanism. How this helps us is, first of all, it helps us reduce the number of tasks that Dask creates. So it's no longer n log n, if people here know complexity notation, but it scales linearly with the number of input chunks or output chunks that we have, keeping task graphs at bay. And also, this system uses disk storage to store all the data, and to do this very explicitly. Previously, Dask would have just filled up RAM, hoped that that data spilling would have worked in a way that prevents an out-of-memory error. But that worked sometimes. Sometimes you actually had some problems. So it wasn't a great mechanism. This here works, is much more stable. So yeah, I'd say let's take a quick look at how much better this is. For this, let's just process a data set of 1 terabyte. It's not too big, but it's a decent amount of data. The problem was when I tried to do this and prepare a demo, I chose a scheduler with 64 gigabytes of RAM, which is a lot more than I'd usually pick. But yeah, nothing worked. It completely ran out of memory. The scheduler just died because we submitted way too many tasks there, because the old task-based mechanism did not scale. Well, if that doesn't work, I still want to show you a comparison. Let's actually pick a size where task-based shuffling has a chance. And that's, in this case, 100 gigabytes of data. So I've prepared a small video for all of you here. Saves me the hassle of spinning up clusters. So yeah, we just submitted the computation. Once again, it'll take some time for the computation to arrive on the cluster because the cluster is based somewhere on the East Coast. My laptop at the time was located in northern Germany. Data transfer isn't the fastest. So 1 or 2 seconds, I think, around 30 seconds it would appear. Ah, that was actually a minute. Well, sorry. So on the right, we see P2P rechunking. First thing we see is that it submitted data much earlier than task-based because the graph size is smaller. If we want to really look at this, we actually see this is like 55,000 tasks, whereas this here is 150,000 tasks. So like factor of 3x doesn't sound impressive, but once again, keep in mind that task-based scales non-linearly, whereas P2P scales linearly. So like at much larger data sizes, this difference will become much larger. If we let this run, we'll see that, once again, I said this here works in constant memory because it writes data to disk directly. Here we see memory build up over time. We can actually like go a bit forward in the interest of time. We still see here there's memory building up. Eventually, yes. When things are yellow, we're actively moving data from memory to disk. So that's what we're seeing here. This is still the same amount of memory that we started with. I'll stop this here. It shows the effect. Once again, this rechunking is much more stable, so hopefully people will have a better time with this. Second problem I want to talk about is downscaling. Downscaling is a computation that essentially helps us to smooth data along the time axis. And if you just look at what's being expressed here, it's 2 rolling means. It doesn't seem too hard to do, right? Also, the data set we picked is like 26 gigabytes. If you had a beefy machine back at home, you could probably also fit that into your local RAM even. So how hard can it be to compute this in Dask? Well, the answer is it has been pretty hard. If you just used that computation in the past, you would have seen that Dask warns you about this thing where slicing with an out-of-order index generates 30 times the amount of chunks that we had at the beginning. That's pretty bad. I just told you that having many tasks is bad, many chunks. That's not a good idea. That doesn't help us scale. So if this is about things being out of order, well, let's do sorting. It's expensive, but maybe this helps. Actually, this is much worse. So that's also not a good idea. With this, we went back to the drawing board and we then, oh, actually, yeah, just to tell you the scale of the problem. We started out with roughly 180 chunks. We ended up with 67,000 chunks. So even if you just multiplied this data by 2, this would mean we'd have another 67,000 tasks that we have to send over and that we have to compute. And those are tiny. Like recommendations for Dask in general are like, use 100 megabytes per task maybe. Definitely not 400 kilobytes. So we went back to the drawing board. We re-implemented the algorithm. And essentially what we tried to do and what we achieved doing is roughly keeping the chunk sizes the same. We see this here. This started off with 180, 140 megabytes per chunk. Roughly doubled here because the chunks were a bit smaller, but this is much better than before. I have a demo for this, but in the interest of time, I'll skip this. I'll just show you one tiny bit out of this. And this, if I choose the old mechanism, we see 370,000 tasks. That's pretty nasty. If we scoop forward, we also see all of this white space here, which means the workers aren't really doing anything in this case. They're just waiting for new tasks to appear. So let's quickly talk about geospatial benchmarks now. Why we are interested in them, and why you should also be interested in them. For this, let's talk quickly about the story of Dask data frame. Over the last year, we did a pretty large revamp of the data frame API. And yeah, a year back, it was honestly pretty shitty. Like, it couldn't do most of the things that your average SQL engine can do, all the optimizations that are in there. It just did literally what you told it to do, and that was usually not the most efficient thing. So we decided, okay, we need to revamp this, we need to improve this, but as usual, there was way more stuff to do than engineering time we had. So we needed some sort of function to decide on what to actually focus on. And luckily for like tabular data, for data frame data, there are quite a few benchmarks out there that tell us how long our computations take. So we picked the TPCH benchmark in this case, which is an industry benchmark for analytical workloads, analytical queries. And with the help of that, we were able to decide on where we'd see the biggest gain in terms of end-to-end performance for customer workloads. And we see that over time, we went down by, well, pretty much a factor of 20x in terms of performance. Like, we're now 20 times faster than we were a year ago. Unfortunately, there is no real industry benchmark or any performance benchmark for that matter for geospatial data that I'm aware of. So we want to build it ourselves. What does that mean? For us, a good benchmark is, first of all, focused on end-to-end workloads. We can benchmark stuff like rechunking to make sure that it gets faster, but we've seen that end-to-end workloads are the most interesting because they also show the interactions between different parts of computations and how they might actually be fairly complex and not what we'd expect. Once again, since this is about distributed computing, we want those workloads to work at large scale. So if it's on megabytes of data, we don't care. If it's on terabytes or hundreds of terabytes or even petabytes of data, we are very interested in that. And most importantly, this has to be representative of real work. That's also where we start to have a problem over at Makait, because we're not geoscientists. We're experts in Dask and the deployment of Dask. But we don't want to build up some made up benchmarks in our ivory tower that do not reflect reality at all and then optimize for something nobody cares about. But instead, we want to optimize for things that users actually do care about. So yeah, I'm asking the geoscientists in the room, if you have some workload that you care about, or generally also people, if you have something you do in Dask that you care about, let us know about this. And for geospatial workloads, actually, please help us to create a benchmark for your workload. We want you to help Dask help you. So yeah, with that, I'll just go to a quick conclusion. What have we learned today? What have we discussed? First of all, Dask and Xarray together are a pretty cool power couple that help you scale your data to terabytes. But it's kind of limited at terabytes. We want it to become better. We've started doing that, and geospatial benchmarks will help us make further improvements in the future. So once again, if you care about something, tell us you do and propose a benchmark. Thank you.
So we have time for a few questions. So if you have questions, raise your hand. Yeah.
Hello.
Hi.
Thanks for the talk. I was wondering, could you tell us a bit more about the barrier, this concept that you introduced that seems to reduce the computation for
Yes, of course.
the number of tasks in particular? Can you explain that in layman's terms, possibly? Thanks.
In here, you mean?
Yes, that's
Yeah.
right.
Basically, so Dask is based on a task-based paradigm. So any output it produces that's a single task, which means that in this case, we would split up this one chunk into very many, very tiny pieces that we could reassemble to create this thing. And that's nasty because, yeah, as we see, like this totally explodes. What we've done now is essentially with P2P shuffling, we have bypassed this paradigm. What we're doing is essentially we just start some computation in these input tasks. They totally do something different outside of your normal Dask. And we use this barrier here just to coordinate that, well, at this point, we know when this task runs, we know that all the inputs are done with their work that they do in the other subsystem that we've created. And at that point, we can then start loading the output data out of that subsystem. That's
Actually, I have a follow-up questions on this point.
Sure.
Does this peer-to-peer rechunking mechanism, is it some kind of private API of Dask, or could a user use the public API of Dask to either re-implement it from scratch or implement a custom variation of it? And which kind of API it is? If it is.
There are a few classes in the shuffle submodule that are technically speaking right now private within Dask. It's mainly because we are not still sure yet what the best way of abstracting this out is. So if you need to re-implement this for something, it would be wise to take a look at this and let us know that you want to do this, and then we should probably just talk, because we've started abstracting this out, but things might change, and also things might not fit the way they're supposed to, because right now we have just like two variants of these. One is for data frames, one is for arrays. Maybe the abstraction just sucks, I don't know. But yeah, just let us know.
Thank you very much for the talk. So you just mentioned here how you can circumvent the issue of creating too many tasks, so the task would explode essentially. But another issue that I've encountered with Dask is when you start with a good chunking, like it fits nicely on your, as recommended by Dask, but then somehow in the middle you do auto projects or something like that that completely explodes the size of your chunks, and you have no guarantee a priori in Dask that the memory budget will be maintained throughout the pipeline, and you cannot really predict this. So is there any work being done within the Dask team to kind of cap the memory budget throughout the pipeline?
I think an explicit capping mechanism might be difficult, because that also just depends on like the individual function that you run. But I think what you're talking about is also something where the API that uses like Xarray suddenly starts exploding things, and that's something where I would ask you to provide a benchmark. Because I've literally just been implementing a benchmark the other day where I started off with something that was like 4 megabyte chunks, like very small. And then all my work has just died in the middle. I figured out today now why that is. That is because it suddenly created like 15 gigabyte chunks. Yes. My workers have like 8 gigabytes of RAM, so that obviously doesn't work. So yeah, provide a benchmark, propose a benchmark, or at least tell us like where you've seen those issues, and then we can work together on that.
Yeah, maybe it's actually the same question. I'm not sure. So I tried to use Dask to do some processing of VMS, so geospatial data, so identifier of the boat, latitude, longitude, time, and I had to compute like speed. So I would do a self join on the like one point, the other point, and then compute the speed and such. And I tried to do that with Dask, and it was not working at all. It was out of memory. Maybe that's actually the same thing he was talking about. I'm not sure. Does this P2P chunk may help?
If you're doing a join in there, this could actually help, yeah. I haven't done tried it with too many self joins. There might also be like some other issues in there, but it sounds like this would help to reduce the memory load that you have in general on the clusters. So yeah, I would think so.
Yeah, it seemed to me like the partitioning was not really working well.
Yeah, I think that it should help.
Okay, so we are running out of time. So thank you very much again